Maybe I should have watched this either. Okay. So welcome to the video. So today we're going to talk about traversals of trees. So remember we were talking about binary trees. We talked about the common types of trees. We had a full tree, a complete tree, a perfect tree. Difference of them being that a full tree has 0 or 2 children. A complete tree has every level full except the last level, and those last level, if it's not full, has to be all the nodes have to be shifted to the leftmost as possible, so you can't have an empty spot. So like this is okay, and so is this. But what would not be okay is like this one's missing or something. That wouldn't be okay. That would not be a complete tree. And a perfect tree is every single level is full basically, and the leaf nodes are all at the same level. That's actually a better definition of that as well. All the leaf nodes are at the no, because if you could also do something like this, and that's not a perfect binary tree. So I suppose they have to have 2 children, and in addition to that, all the leaf nodes have the same level, because then that forces that to be that way. But anyways, so here's the thing. If I want to represent a binary tree, I can just be like, well, let me just draw it, in a test. I can be like, here's your binary tree. Like that. But in a computer, you could actually do the same thing, right? You can use pointers and represent it like that. But how you represent this to actually give it to the computer initially? So like, you got to give it a list of some sort and then build it from that list, right? Because you could try to do like ASCII art, but how are you going to parse that? How are you going to build this tree on a computer, give it some data? Like I told you, just like build this tree. How would you do that? Well, what's that?
The middle element to be the starting point.
The root, you mean?
Yeah.
Well, yeah, that's a good starting point, I suppose. You pick the root, and then from there, maybe you give it the children of the root, and then from there you give it the children of those roots, and so on. And it turns out that it's quite a tricky problem. And the best way to do it is using traversals. And there's 4 traversals that we know. And actually, it also turns out that a single traversal is not enough. You usually have to give 2. Level order traversal being the only exception where you can give 1 as long as it's a complete tree. So let me just go ahead and write down the traversals first that we'll talk about. So we have level order traversal. And what the word traversal means is how you visit the tree. And as you're visiting it, you're printing out the nodes. We also have in order traversal, post-order traversal, and finally we have pre-order traversal. And using these 4 traversals, typically a combination of this one and this one, or this one and this one, or just this one, with it being a complete tree, you can build a tree. So let's talk about the level order traversal first. The level order traversal of a tree is you writing the nodes in the order that they appear by level from left to right. So for example, this is level 0 or 1, depending on how you're counting the levels. But this is, either way, it's the first level, right? The next level is B and C. What would be the third level? Just D and E. And then the next level? GIF. So when you're building the level order traversal of a tree, once you have defined which nodes are on each level, you just print them out from left to right, top to bottom. So that would be A. I don't think I have space to do that there, so we'll just scoot this down a little bit. That's going to be A, B, C, and then D, E, And then the last level, GIF. Oh. Okay, so A, B, C, D, E, G, I, F. As you can see, it's just the order of the levels that they appear in. Now, let me tell you why that's not enough, because this is not a complete tree, right? C doesn't have child. If it did, then it would be okay, right? If we had a child here, in fact, maybe I can, well, different color I haven't used, gray. So if we had a child here, right there, oh, that's really hard to see. Maybe, can you turn the lights off? Thanks. I keep forgetting to do that. Yeah, that's better. Awesome. So if we had a child there, it's a little darker too. Then it would be okay. Actually, no, we need one more, right? B, yeah. Now we're okay. Right now it's a complete tree. So if that was the case, then we wouldn't have problems. So what would be the traversal in that case? Well, it would be what we had before. So A, B, C, D, and then we also had E, G, I, F, but we have now these two missing ones, right? So I can use some sort of flag or some special, not flag, what do they call it? Delimiter, wildcard, one of those names, I don't know. But in this case, just a variable, which I'm gonna use, actually I'll use the one that I used in the assignment. I use %. I don't know how I picked that, I just did. And so that signifies that that's an empty node. But I just fill it in so that it's not empty anymore, but when you're actually inserting it and you see a percentage, then you don't actually create a node. It's just a stand-in per se. So now this is a complete tree, and you can actually only build one tree out of this. Let me give you the example where you could actually build more than one tree out of this one. I'll do it just down here so we have space. D, E, that is also a level order traversal of that, right? That's at one level, another level, another level, another level, another level, another level, and then those two are another level, right? That tree is not the same as this tree, right? However, if I know that this level order traversal represents a complete tree, it means that I cannot leave empty any nodes that are not in the last level. Therefore, I cannot insert C until I have something here. And if it's a complete tree, then that means B has to go here. Okay, let's try to do that with this version without the wildcard. A, B, C, D, E, G, I, F. That's not the same as this either, right? Where does it go wrong? It goes wrong after this one. These all go wrong. However, if we do the version with the percentages, then we have to put those two right here where we put them, therefore fixing that problem. So as you can see, as long as you make it a complete tree, and even if it's not, you put in some sort of placeholder for that, then you can build a tree out of a level order traversal only. As you will see next class, you don't have to do any sort of placeholder wildcard BS if you're strictly building the tree from two traversals, which are in order and post-order, or in order and pre-order. And whether or not you can build it with just the post and pre-order is a question for your write-up that you will figure out on your own. So. I'll leave that to sort of your own practice. But anyways, for now, let's worry about how to even build these three because we haven't talked about that. So, but first, and also by the way, another name for level order traversal is breadth first search. And we will talk more in detail about breadth first search when we talk about graph theory, which is why in the assignment, I actually give you the solution to breadth first search in the skeleton code. And all you have to do is implement the other traversals.
Wouldn't the percent signs throw it off and not let it be a complete tree because the F has to be the most left?
Yeah, that's what I was wondering.
Even if you put a child at B, then F would have to go to that child.
In that case? Oh, that's right. I never added those additional ones. My bad. Yeah, we need to have more empty nodes in here. Problem solved. So yes.
Okay.
Now it's a complete tree. So
Does E also do a node?
no, because it's the leftmost. So that's the rightmost thing. There's nothing in it. If
we wanted a perfect tree, it would need one.
well, lies. Perfect trees. The last level doesn't need to have to be full. Just all the way to the left.
Isn't that a complete tree though?
Oh, perfect. You said perfect. My bad. Yeah. If you want a perfect tree, then yes. No lies. Truth. Yes. I don't know why I heard complete in my head. So, yes, if you want a perfect tree, then yes, you can do that. But for implementation, a complete tree is good enough, per se. When we talk about heap sorts, we'll be using also a complete tree. So, I'm glad you caught that. I guess one way to check that, safeguard yourself, is to count the number of levels or the height of the tree. So in this case, we have 1, 2, 3, right? Or if we're counting from 0, it would be like 0, 1, 2, 3, 4. But if we're doing it, whichever we're doing it, we can either use the formula 2 to the h minus 1 or 2 to the h plus 1 minus 1. This one we would use if we were counting like 1. Sorry, we're doing 1, 2, 3, 4. Or if we're doing it like more naturally, like 1, 2, and 3, then we can use that formula. So let's use this one because it seems more natural. 2q plus 1, 2q plus 1, yeah, so 2 to the 4th, which is 16, right? Yeah, 16 minus 1 is 15. If you were to use the other method, you would see that 2 to the 4th is basically the same thing, 15, right? 1 minus 1 here. As you can see, both give you the same answer. It depends on how you're counting your height. So before we had 1, 2, 3, 4, 5, 6, 7, 8 nodes, and then we had, I think, 2 children, so we had 10. That's bad because we should have had 15, right? And we only have 1 empty spot here. Now that we added the extra children, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're okay, basically. So I guess that's a good safeguard to sort of catch what we catch, but you guys got it, fortunately. So are we okay now on level order traversal? Okay. Let's move on to something more interesting. I guess we'll have to do a new one. Because I guess I kind of want to copy the same one, but whatever. I think I'll make it as close as I can. So I think it was a D here, E there, and then I think maybe like F, G, I. Let's put another letter there. H. Yeah, I think that's good. What I'm trying to do is have variations so you can see all possible cases. Let me clean my nose for a second here. I'm still sick, so don't get too close to me. Okay, so which would you like me to show you first? Free, in, or post? What's that?
Just go in order.
You want to do in order first? I mean, or do you want to go in order?
In the order that you wrote. The order that you wrote.
That's what I just messing. So I don't even know what order I wrote them on. Well, I wrote in order first, so that solves that. Okay, so in order. Well, here's the little trick to remember these, and I'll put that right here actually real fast. At least this is how I learned it, and it's kind of weird that the letters that I use, but I do. Let me write it first, and then I'll explain it. This is how I learned them. Left, root, right, left, right, root, root, left, right. I know I used R twice. One of them is bigger to sort of remember which is which. Maybe not the best case. Maybe the word P is more useful. Fortunately, it's too late for me. It's just burned into my brain that way. So I can't ever change that.
Can you explain again? You said left, root, right?
Yeah, so the L stands for left. The R stands for root. Also print, I suppose. And then the R stands for right. Frankly, if you have a clean slate, try to remember it with a P instead of an R. I think that's better, but there's no point in me trying to do that because I know that I'll go back to the R very fast. So I'll tell you what that means though. But anyways, that's how I remember them. And that's how I recommend that you remember them in a test or something like that. So we are doing left, root, right first. And notice that the root one I write bigger, so that's how I know that that's different. So what this means is traversing the tree means we're going to visit every node of the tree in a specific order, which is going to depend on the traversal that we do. We always start on the root, whichever traversal we do, whether that's level order, pre, in, or post. They're always starting at the root. So we're always going to start at A. When you see the word left, or the L, with the letter L, that means go to the left child. When you see the small r, it means go to the right child. When you see the big R, it means print that node out to your output per se. So, in this case, we start at the A, and for each of them, it's recursive. And so, I'm just gonna, at least for the first few examples, I'm gonna kind of show you for each one that we're gonna go through those 3 steps. Left, root, right. So we start out with the A, and we start out with the left of that. That means go to the left. So immediately this stops, and you go to the left child, if there is one, which there is. So now you're at B, and you're actually doing the same thing. You see the L, and then you gotta go to the left of that. So you go to the D, and that pauses too. Left of that, there is a left, so you go to the H. Oh, I don't like that arrow better. Now you're here. You're at the H, and you're at the left. You try to go left of that, but there's nothing, right? In actual implementation, that's a null pointer, but there's nothing there. So that's fine, nothing happens. Then you go to the root, which means to print it. So now, in your sort of output traversal here, we have our first thing to print. We print out an H. From there, we got to go to the right. But there's no right, so nothing happens. Then you're done. When you're done, that stack sort of returns, that function returns, and you go back to the previous one, which was right here. So you're back to here. But now, you just came from there. So the next thing you do is you do the R, which is to print out the D. So it's the second letter that you printed out so far. And then you're going to go to the right. But D has nothing on the right, so therefore nothing happens. So then you're done. So you go back to the B that called it. So that, I guess you could say that's an arrow here, arrow down, and arrow back to B. Next, you're going to print out B, because that's the next thing to do there. And then you got to go to the right. In this case, there is a right, so you take it. So now, I'll cross these out so you don't get confused. We go to the E, which is the child, the right child of B. Okay, start there. We got to go to the left of that. There is a left child, which is G. Okay. Now we got to go to the left child of G, but there is nothing, so nothing happens. Then you got to print out G. Then you got to go to the right of G, but there's nothing, so nothing happens. So then you go back to E. And now you do the center, which is the root, which is print out. And then you go to I. There's nothing on the left of that. You print out the I. There's nothing to the right. You go back to E. You already printed, you were on the right call of E. So then you go back to B. You were on the right call of B. So then you go back to A. Now you print out A. We run out of space, so let me move them to the next line here. Huh, where did that R come from? Here we go. Now we have space. So we go back to B, we print out, we go back to A, we print out the A, and then we got to go to the right of that. So I'll just continue that down here. So we got our A, left, root, right. We did that, and now we're going to do that. There is, of course, a child to the right of A, which happens to be called C. So we go ahead and we do the exact same thing there. So we are going to go ahead and go to the left of that, but there's nothing. Then we print out C. And then we got to go to the right of that, which there is something, and that's F. So when we get to F, there's nothing there. We print out F. There's nothing there. We're done. We go back to C. C, we're done. We go back to A. A, we're done. We're done with the entire thing. You finish the traversal. H, D, B, G, E, I, A, C, F. And that's it. Questions? I want you to, of course, right now we're not doing binary search trees. You're just doing binary trees. But let's do an example really fast of a binary search tree. So 8, what can be right here, by the way? Or equal to 8 too, technically. But yes, less than or equal to 8. So let's go ahead and do 6, 4, 7, 9. We seem to have faced an issue here. I guess that. Okay, that's okay. Duplicates are nice to have. Maybe one more. 5 there. Okay, let's do the in-order traversal. This time I'm going to do it rather quickly. I'm not going to do this whole nasty stuff, which is quite simple. I'm just going to actually draw an arrow how we start. So you start out with the 8, and you got to go to the left, and then you cannot go left anymore. At that point, you print out the root node, and then you go to the right, cannot go left, print out the 5, cannot go right, go back to 4, go back to 6, print out the 6, go to 7, print out the 7, go back to 8, print out the 8. From there, you go to the right, but before you print out this 9, you got to go to the left. So you get here, nothing there, print out the 9, nothing here, come back. Now we print out this 9, and then we go over here, nothing here, print out the 10, nothing there, go back here, we're done. See how fast that is when you kind of get that going? So just got to practice it. What can you tell me about that traversal that I just printed out? It's in order. Yeah, look at that. It's called in order. So whenever you have a binary search tree and you do the in order traversal, it's going to give you the sorted list back. Another sorting algorithm you just kind of learned. Let's analyze this a little bit, like time complexity. Remember what I said about the height of a tree? The height of the tree can be anywhere from n with n elements. When is that the case, by the way? When is the height of the tree n? When it is a linked list, which is a degenerate tree, which we also call pathological tree, and which we also named in Discord to be the anime tree. Yeah. So ultimately, that's the worst case scenario that our thing basically becomes a linked list, right? And a linked list takes n time to insert something into a sorted linked list. So here's the thing. If we have it either complete or we have a balance in general, a balanced tree, we have a height of log n. That means that every time that we insert something into a tree of log n, it's going to take log n time, right? So inserting one element into a log n tree takes log n time. We got to insert n elements of that. So n times log n, because each one's going to take log n. That means to generate a binary search tree that is balanced, as long as it's balanced, as long as I can guarantee that it's balanced when I'm inserting, it's going to take me n log n time, plus my traversal, which is just n time. So I can tell you that my algorithm here that I came up with for sorting is going to take n log n plus n, which we know that n is just nothing, so really just n log n time. There's one caveat here. And what is that? What's the catch? What's the catch that I said?
It has to follow the format.
It has to be log n height, basically, which means it has to be balanced. How do I maintain balance and not making a degenerate tree, basically? Well, it turns out it's tricky, because if you just insert in any order, it's unlikely that you're going to keep, unless more than likely it's not going to be like a linked list per se, but it's not going to be super nice as it's balanced. It's going to be like halfway. So it might be something like, it looked kind of nice, but then maybe like one side kind of got nasty.
So is that why we have to do like the left and right rotation?
Yes, so that is part of the AVL tree algorithm, or red-black trees, and that is one way that every time you insert, you can rotate things around to make sure that you maintain that log n property. Because every tree starts out as log n, because technically an empty tree, right? It's an empty tree is okay. One node is okay. Two nodes is okay. When you get to 3 nodes, that's when you risk it already being unbalanced. If it's a degenerate tree, basically just link, like this. That's already bad. You want to rotate that by bringing that up and making that the root. Because it's like 1, 2, 3, and it becomes 1, 2, 3. But those are rotations. That's part of AVL trees. That's next week or after, hopefully next week. Yeah, next week. So, but before we can get there, I wanted to just sort of introduce that concept that using the in-order traversal will give you a sorted a sorted list in potentially n log n time if you have it balanced. So that's kind of cool. Another sorting algorithm to kill Sally with, basically. All right. Okay, so let me go ahead and write to you. So I think at the beginning of class, I said that you asked me if there will be any code in the tests, and I said there will be one case where code is just much easier to explain something, and that's exactly what I did, the in-order traversal, preorder, or postorder. It turns out that writing the pseudocode, or just writing the code actually, the C++ code for doing it, is so much easier than trying to explain what I just did on a test. So let's go ahead and write the code. In order, yeah, because that's the only one that I've really shown you. But you'll see that the code's going to be very similar for the other ones. Yep. I wonder where I learned the cur thing from. That's another thing that I just learned at some point. I always use cur. I think that's just a general thing.
Geeks for Geeks.
Is it on Geeks for Geeks?
Geeks for Geeks, Discord, or not Discord, what's the one called?
No, but I'm saying, do they use that in that?
Yeah.
Okay, so I guess it's maybe. Oh, at some point, I just got used to using cur as my current pointer. So the first thing is, I don't trust other people's code. I don't trust when they're going to call my function. So the first thing I want to do is check if they called the null pointer on that to avoid null pointer exceptions. So I don't want to risk it. If cur is equal to null, just get out of there. What does that mean? That you visited an empty node, basically, a null node. Okay, now that we took care of that, we can actually do the algorithm. So this is left, root, right. So we got to go to the left first. How do we go to the left? Quite easily. Just call the same function again. But instead of passing a cur left. And this is assuming that we have the data structure that I showed you where we have data, left, and right. These are pointers. And this is either a pointer or like an actual variable. I'll show you both ways, I suppose. So yeah, just cur left. Bam, done. Next, we gotta print out the node itself. Cout. Cur data. In fact, maybe to make it nicer, we put a comma and a space, and then flush it. Okay? Yeah, you remember that from 202. Yeah, very briefly we covered it. I know we covered it because you guys asked about it.
A little bit.
We didn't cover that.
For those who didn't take it.
Yeah, no, that's
For
right.
those who didn't take it with you.
Okay, so flush, what does this do? First of all, hopefully you guys know that one. That's end line, but that's, so what does it actually do?
Line removes.
It does a line feed, but also flushes the stream out. So you're getting, what is this flushing thing going on? Okay, well it turns out the following. When you're writing code in C++, and your program is running, like you compile it and you run it, and you have a line feed, or you just have a print statement. It's like you're working, and you got your OS as your assistant. And you're like, OS, print out the following bubble sort solution or something. And then you tell the OS, and the OS is like, sure, I'll take care of it. And then you don't wait for them to actually take care of it. You keep working. And then you're still sorting bubble sort. And then you're like, I'm going to print out the next thing on my iteration of bubble sort. And you tell the OS, like, OS, I got more stuff to print. And then the OS kind of keeps a list of things to print. But you're not guaranteed that it's going to print them out immediately. It's also possible that if you're running so much code and so much printing, that it might print things out of order too. There's no guarantee that it's going to print it out continuously, like the buffer will flow properly. Flushing, and also here's the other part. Suppose that you finished doing bubble sort, and now you're doing the linked list bubble sort, and you crash. The moment you crash, the OS is like, he died. I don't need to do anything else. Like, I'm not getting paid anymore, I guess. My boss died, so I stopped. So even though you already had a list of things to print out, they may never get printed out. That's if you're just outing stuff, using line feeds, and that's it. End line and flush, in addition, end line it has the line feed, but flush, that's like you saying, okay, I need you to print out core data. And I'm going to actually stop the program execution and wait for you to confirm to me not only that you're going to print it, but that you have already printed it out. And once you tell me, like, yeah, I'm done printing it, then they'll actually restart the program and keep going. So it's like you have an attitude, you're like going to wait until they finish doing it because you don't trust them. So yeah, that's pretty much what flush do. Flush will basically halt execution and wait until it prints out. And that guarantees that, for example, things get printed out in the right order. And furthermore, which you shouldn't, oh yeah, we need to talk about that. Remind me of the class to talk about what's happening on Thursday. But if you shouldn't be doing this, but if you're printing out, if you're debugging using print statements, and you're saying like, cout, I have reached this line, if you don't put an end line or a flush, it's possible that you actually reached that line, but it never got printed out because you crashed before that. So make sure you put that flush or end line to guarantee that if you got to that line, it will print that line out. Otherwise, sometimes it might print it, sometimes it might not, and that's really bad because you're like, what the heck? Sometimes it's reaching this line of code and sometimes it's not. You're in the worst place than you started with.
Dude, that happened to me yesterday. I was so mad.
Well, now you have to send it that, right? Because you can use flush. Do you have a question?
Is a flush a function call, or is it like a keyword?
It's like cout, so not a keyword because when you think of keyword, that's like a reserved keyword.
Like endl is not a keyword, right?
Right, they're not technically, but I mean you could name a variable endl as long as you don't say using namespace std.
So
because you would do like.
So flush is all like flush with the capital letters. All we have to do to do that.
It's just part of. It's just to use it. You just do like cout this. What is that? The extraction operator. Flush. So yeah, it's just like endline. Instead of endline, you put flush basically. But I don't know if it's technically a keyword. It's just a variable. It's weird. Printing in C++ is weird. You know, there's no print function and things like that. Because printf is C technically. But yeah, just to use it, just C out, blah, 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 flush, or endline. The problem with endline is that you're adding also the line feed, so sometimes you don't want that. But you still want to make sure that it prints out. So, yeah, you learned something new today. Or something you already knew but you forgot. Okay, so back to this. After printing out the node, then we want to go ahead and print out the right side. So, the right child, so the same thing, just occur. Right. And you're done. If you want to make it a little bit more efficient, you can wrap each of these in a if statement saying if cur right is not equal to null, call it. That way you don't have a useless call with null. But even if you do, this will take care of it. But it's slower because there's still that stack being created and function call being done, going to the function, seeing that you have nothing to do, going back to the other function, that's time, right? And if you're running this with 10,000 ships, then yeah, Bobby dies, or Sally. So, questions about that code?
You don't need to add a C out, right, after the cur right?
Yeah, I was gonna ask that. Shouldn't you printing out right after, right?
No, because I'm only printing out in the middle.
Oh yeah, because it'll call itself again, it'll wrap
Yeah,
back around if there's
it's recursion.
something down and print.
It's recursion. See, this is actually a really, really good case of recursion where like, iteratively, I would be stuck for a while thinking of how to code this iteratively. Without a stack. I need a stack, I think. So this is like 3 lines of code. Explain it, if I ask you in the test, explain the insertions, explain it in order traversals, you can just write those 3 lines of code and you're good. So,
Just so I know for my own personal sanity, is it possible to code those sorts in a manner like this, in sorting algorithms, where it's super concise? Because my shit was a hot mess.
I don't know, you can use dot sort. I mean, no, there's a limit to how concise you can make code before it becomes unreadable, right? And even so, like quick sort,
Got it.
bubble sort, yeah, sure, but then again, it's just like 4 lines of loops, 2 loops and two if statements, and that's if you have the swap variable stuff. So, anyways, I think you get the idea, but I'm gonna show you. Before I even show you what the other traversals are like, I'm going to show you what the code for the other traversals looks like. Suppose you want to do the preorder. So that's root, left, right. That's the shortcut. What do you think is going to change in this code to accommodate that? In fact, let me make this R bigger so you know that it's that one.
Move the C out.
Move the C out, basically. And you also want to rename the functions, which is something I forgot to do when I was doing the assignment. And then I was confused, and I was like, oh, that figures. Because I copied and pasted it. And I was doing the solution. And there you go. That is your preorder traversal. I like that bracket more. Finally, and then we haven't even done it yet, but like now you know what the code looks like. So you're getting most of the assignment already here. Let's put it this way. Your skeleton code is 319 lines of code. My solution is 360 lines of code.
God bless.
So it's like 40 lines. Yeah. Plus maybe comments and things like that. But that's like real code. Assignment 6.
That's not due till like the 21st.
Well, yeah, but that's only because, like,
3 assignments are due one after another.
yes.
Yeah.
That's why. So you don't want to, you don't want to wait until like,
You know my favorite thing on that skeleton code?
what?
The get data one. This
Get battle?
get data.
Get data.
It's just a getter.
Oh, yeah. Well, I was trying to do object-oriented programming, good practices. I don't know where those parentheses came from.
You took it from.
Ah, okay. There we go. Thanks. Curly brackets are hard. They're hard life. Okay. There you go. That's post order as well. So,
Well, you forgot to change the acronym for Postorder.
the what?
The acronym.
So that's right. Right.
Oh, yeah, I suppose. Yes. Otherwise, people will probably look at this during spring break and panic. Okay. So now you have the code, but I'm still going to show you examples of those too, because I've only really showed you in order. But I thought I'd show you the code so you can see that it's really much the same thing, just different order of the 3 lines of code that you have in there. So as long as you remember your little acronym, at least for me, that's how I remember it. Like I always write that down next to doing it. Like when I was doing the assignment, I just want to make sure that I get them backwards. So do we have any clean? Nope. We'll just make a brand new one. Here, let's do one with numbers for a change. Different numbers, otherwise people will not know which is which. I'm trying to stick to single numbers to not also get confused. Okay, good enough. Did we end up with the same structure? No, it's not the same. Okay, I'm weird. Okay, so pre-order or post-order? Which one you want me to do?
Free.
Pre? Okay. In pre-order, the root is always the first thing you're going to print. And the way that pre-order works is like, as you visit each node, the first time you visit it is when you're printing it out. That's kind of the trick here. So again, you always start from the root in every one of them, even though the root may not get printed in every one of them. In fact, in post-order is the last thing that you print. And in order, it's like somewhere in the middle. And in pre-order, it's always the first thing. But you still start at the root as the first node that you visit. So I guess, even though I didn't state it explicitly, when you're calling these codes, the parameter that you're passing in for cur is going to be what? The root. Just the root. So in main, you would pass the root. So I guess that's a important thing to remember. Otherwise, you're like, what do I pass it on? So, okay. So, I guess for the first, 3 of them, I'll do the little thing here where I do, the colons. And then from there, we'll just skip to that. So, we start out at here. And the first thing, as you can see, is that we actually print it out. So, we are going to keep track of that right here. So we print out the 1. And then the next thing we got to do is go to the left of that. So that's the 2. So we print out the 2. And then we go to the left of that. So we get to the 7. We print out the 7. And then we go to the left of that. There's nothing there. We go to the right of that. There's nothing there either. So then we're done with this. We go back to this call. So back to the 2. So because we just came from the left of that, we're going to go to the right of that. So that's a second recursive call. So we're going to go to the 4. When we get to the 4, we print out the 4. We go to the left of the 4. We get to the 6. We print out the 6. There's nothing on the left. There's nothing on the right. So you go back to the 4. You go to the right of the 4, but there's nothing there either. So then you go back to the 2. You just came back from the right of the 2. Therefore, you just go back to the 1. And now you go to the right of the 5. The 1, sorry. You get to the 5. You print out the 5. You go to the left of that, but there's nothing. You go to the right of that, you find the 8. You print out the 8. You go to the left of the 8, there's nothing. Go to the right of the 8, there's nothing. Therefore, you're done with the 8. You go back to the 5. It turns out that you just came back from the right of the 5, so nothing happens either. You go back to the 1. You just came back from the right of the 1, so you're done. You go back to main, per se. So that's pretty much it. Is that good, or you want me to show another example? Another one. All right. Letters. How about that? I always start with A. Let's just start with a different letter. J. How about let's put my name? Okay. And I know there's repeats, so we'll maybe say 1 and 2 like that. Is there more repeats? Yes. 01, 02. It doesn't matter when we're printing it, but it's just so you, if you're looking at this at home later, then you actually, recording, yeah, then you can know which is which. So a pre-order, we start at the J. So we go J, we print out the J, we get to the O, we print out the O, which is 01. We get to the G, we print out the G. Then we get to the F, and we get to the 02. From there, we can't go this way, we can't go this way. We go back to the F. We already printed the F, but now we gotta go to the right of that. So we get to the N. Then we go back to the G. We go back to the O. Then we go to the E, and we print out that E. From there, we can't go to the left of that, but we can go to the right. So we go to the right of that. So we get the S. We can't go to the right of the S, but we can go to the, sorry, we can't go to the left of the S, but we can go to the right of the S. So we get to the second E. From there, we can go to the left, go back here, we can go to the right, go back there, come back, come back, come back, come back to the O, come back to the J. From the J, we go to the right of the J, and we find the R. So the final thing is J. I'll just do them without commas. And this is 01.
This is his name.
What's that?
I just realized it's your name.
Yeah. Almost my name. I think.
Was that done on purpose or what?
Yeah, I even said it. I said it. Yeah, that's how much attention you're putting.
I didn't hear that.
Watch the video. It's on video. So, yeah, see, for those of you watching, this is what I deal with every day.
That's funny.
All right. So, anyways,
He misspelled his own name.
as you can see, I could hide messages here, right? Like I could do this backwards. I could make it so that like this looking out of order thing becomes my name once I do the traversal, right? That's what the assignment's gonna be. Yeah. It does. Yeah. I was kind of excited when I came up with that. Proud of myself.
He's a James Bond.
Yeah. So we'll go over that. But first, let me do the last one. So now we're at post. They're getting bigger now. So, okay. Post-order traversal. So, here's the thing with the post-order traversal. It's kind of annoying to wearing 2 watches. I'll take this. So, you can think of this one as you're going to go as deep as you can before you print something out. So it's a little greedy in that sense. So, letters or numbers?
Letters.
Letters. All right. Let's write another. Let's write James Bond.
Is it supposed to be right left print or left right print? Is it right left print?
Ah. Left right. Yeah, I flipped those. My bad. Thank you.
See, I am paying attention.
He never said it.
Is the level order traversal of this James Bond? Yes. Right? Yes. Yes. Because we got level. There we go. Okay. Cool. So this is our root. This is what we're going to start with. Well, we passed the recursive function in the beginning. And so, as you can see, we're going to go as deep as the E, because every time we hit the J, we go left, hit the A, we go left, and then when we can't go deeper, we go back, then we try to go deeper on the right, which we can, and then we're like, oh, okay, on the way back out, we print things out. So the first thing on this traversal that you're actually going to print out is the E. From there, we go to the A, but before we print out the A, we're going to try the right side and see how deep we can go. So you go to the S. So you print out the S. You can't go deeper on either side, so that's why you print it out. So I guess the logic is go to the S, but before printing it, check left, check right, and then print it. Go back to the A. Now we went both left and right of the A, so now we can print out the A on the way back. Back to the J. We don't print the J yet. Instead, we go to the right of that, and we find the M. We try to go to the left of the M, but there's nothing. Then we try to go to the right of the M, and we find the B. From there, we try to go to the left of that, and we find the O. From the O, we try to go to the left of the O, nothing. To the right of the O, nothing. So we print out the O. We come back to the B. We try to go to the right of the B this time. We find the N. We try to go to the left of the N, but there's nothing. We try to go to the right of the D, and we find the D. Sorry, right of the N, and we find the D. We try to go to the left of D, to the right of D, and we print. Yep.
So you kind of just print backwards in this one. You go
Sort of.
backwards.
Yeah, you can think of it like backwards. And then on the way up, you print. So you go back to the N, for example, you print the N on the way up, print the B on the way up, print the M on the way up, and finally print the J. As you can see in the post-order traversal, the root is the last thing that you print, whereas in the pre-order traversal, the root is the first thing that you print. In the in-order traversal, it can be anywhere, but more than likely it's going to be in the middle. If you have in an in-order traversal something like this, like I have a big tree here, then it'll actually be the first thing that you print. If you have an in-order traversal that looks like this and there's nothing on this side, just everything is on this side, then it's going to be the last thing that you print. But more than likely, you'll have something like this, meaning that all of this will be printed before the root, and all of this will be printed after the root. We will take advantage of this next class when we're talking about building trees from traversals. But before that, everybody understand post-order?
Why would you prefer using one over the other? Like, why is there so many different?
In order is useful because of the sorting stuff, but pre and post order have, I mean, there might be benefits like, an algorithm requires you to print this order first. It's more because when we're trying to build the tree from the traversals, we need at least the in order and then either the pre-order or the post order, one of the two. So that comes in useful then. But there's tons of algorithms out there, so there might be some that use the pre-order for some stuff. I don't know.
To get around the patent.
What's that?
To get around a patent.
Yeah, maybe. In the assignment, in addition to doing these traversals, was it someone in this class that posted the Harvard final exam?
Oh,
Yeah. So, well, the question there was to use mirroring. And there was 2 coding questions in that. That was really easy. It's multiple choice. But the last section was open-ended. I took the test. So the only question where I had to actually think was you had to take a binary tree and then make the mirror of that. And so, at first I was like, okay, I got to think. I figured it out. But I was like, this is a great thing to put in the assignment. So I put it in the assignment. Yeah, so now
I think I could already figure out like.
it's actually pretty short code, but I don't want to mention it because I want you guys to kind of have that critical thinking.
Maybe just talk about it a little.
No, I think we're
We
good.
barely talked about last assignment, so we got.
We'll talk about the assignment, but anyways, that creates basically pre-order, in-order, post-order, level order, mirror the tree, and once you mirror it, you got pre-order, post-order, level order, and in order. So, yeah. So I guess let's talk about the assignment. But
How about Thursday too?
well, in the other class, I stopped the recording to talk about the assignment.
Just keep going. Thursday.
But the thing is, I was gonna show you the video. I guess I can pull it up here, but I'm concerned about opening YouTube, and I don't know what's gonna pop up out of YouTube.
You trying to hide something?
Okay, that was clean.
Is that your dog?
Yes. I just didn't want some weird recommended thing coming up or something.
Because you watched.
Yeah, I don't.
It is your recommendation.
I mean, what you guys made me watch some weird stuff over the weekend. So yeah, I don't want that to come up. So
All you're gonna see on our YouTube right now is.
all right, so I'll pause this once we get to the part. So this is your assignment 6, Friday afternoon. can I? There we go.
Man, we're supposed to read all that stuff.
Well, you can read it on your own. But it's also on the canvas, so you don't have to like read it directly from the video. So your mission is you're working for Q Branch, and everybody's seen James Bond or know James Bond. Q Branch is the tech people that make all the gadgets. So your mission is that and James Bond usually wears a watch, and they do like fancy things, right? And since he started being sponsored by Omega, he wears Omega watches. But so ultimately, his watch can like shoot lasers or decrypt things. So in this case, you're going to add a functionality. It turns out that the bad guys, the Spectre organization, is encrypting their messages using binary trees. And so your mission is to implement a way to build. So the way they're sending the messages is they're sending the level order traversal of the message, and making it a complete tree by using a percent to fill the missing branches or the missing nodes. And so when you go ahead and you build the tree, you can do it just from the level order traversal. And once you do that, your job, and I gave you skeleton code that already does that. You don't have to build the level order traversal. What you have to do is you have to do the other traversals, the in order, post order, and pre-order, and then do the mirror of everything, and then print them out again, in order, post order, and pre-order, and level order. And so doing that, you can see all the possibilities. So yeah, you'll see that in a second. But ultimately, here let's forward a second here. Let's fast forward. Okay, here we go. So you see all these messages down here at the bottom? Those messages actually are all of them except the first one. The first one is just garbage, and I just did it as a test. But the other ones are real messages. And when you do the traversals of all of them and you print all the traversals out, one of the traversals will make sense. It'll be an actual message. And so your job is to put that in your report, basically. So you have to implement this so that James Bond can intercept messages like this in the field and listen to the enemy's chatter using his Q watch. So, yeah, it's pretty cool. You gotta be creative. And so here I... Have you guys played GoldenEye? Have you played GoldenEye?
Yeah.
You know how the AK looks like a pencil, right? So that's why I put a pencil. It's a school version of the thing, so then you got the Q watch. And so here's your opportunity to regain some of those test points back. You can get up to 5% back. In addition to doing the assignment, as I have it right now, I hard-coded just like a watch that's just like, it's always making this direction, and it has a time that it actually pulls from the system. If you can write a function that can actually generate the right lineup for the dial for the hands of the watch that represent the time, then you get 5% back on your test.
We don't even know our grades yet.
I got midterm this week.
That's just, do you feel lucky kind of thing. So one easy way to do this, but horribly painful way, is you could make a massive if switch statement and hard code all the possibilities.
All the possibilities.
It's only 60 for the second, which I don't think you can give 60 in there, so maybe not even that many. But yeah, 60 times 60 plus, it's about 180 possibilities, of which maybe you have to generate like maybe 100 of them. But maybe you can find a better, smarter way with math.
But we have to find the right characters and come up with somehow.
Yes,
some
that's
way-
the other
Yeah.
nasty part. So I didn't say it was easy, that's why I took the credit. But anyways, the part of the assignment that I coded for you, all main is done, and there's a bunch of test cases in main so you can actually get your code properly tested. And
I'll pass on that.
I can't zoom in on that, but it looks, you can read it, and also it's on the output file. So this is like me running the program. So you got a message saying like, good evening, Mr. Bond, your latest Q watch has these features on it, blah, blah, blah. And then there's 5 messages, which are the ones that you saw before, that you can try running on this program, and you will generate level order, in order, pre-order, post-order of the message, or then mirror the tree and then generate again level order, in order, pre-order, and post-order. And one of those, when you're looking at it, will make sense. Like it'll actually be a message in English. The other ones would look like garbage.
So you want us to flip, when you say mirror it, you want us to flip left and right pretty much?
It's like, if almost the same. It's literally just look in a mirror. Like put the thing next, so put your phone out and look at like the reflection of it, and that's what I mean.
Like we have to like physically do that?
Yes, you have to write a function for that. That was a Harvard question, so we want to show them we can do that, right? They did it on their exam. You have time at home to do it.
What if we upgrade his watch to be digital?
That's already done. That's working. That's actually working. I mean, it's not refreshing every second, but when you run the program, it pulls the time you run it. So like I ran this at 5:24 p.m. So.
It'll tell you guys to use it late.
So.
Turning in the homework.
Yeah, that's pretty much the assignment. So, you know, you get hyped, get one of these for like $10 on the internet. You know, he's got one. It's cool. What's that?
Can we make this one 600 points? I can get some of my points back.
Okay, James.
Well, here's the thing. This is worth, I think, 400. But then the next one, which is assignment 7, is this assignment, but the only difference being that instead of me giving you a level order traversal that automatically builds the tree, you will have to build the tree yourself using a pre-order and in-order traversal. I even already made the picture for that one. This is like, Spectre has updated their thing to be more secure now. Now you need 2 of them. So,
It's like the Inception.
yeah. So you need that to get this working. You gotta make sure you get this one done. The functions that you have to do primarily, that's really loud, is
No, one of them is.
you have to do the older traversal sex level order. That one is done for you. And the inserting. The inserting is tricky. There's one thing that I want to show you for the inserting. Notice something about like, here, let me just do another tree. That's just empty notes, okay? Which we can use whatever I use in the assignment, which is a % sign. The level order traversal of this, which is what you're giving in, would be this, right? Okay, let's index these in 2 ways. Like that, and then also like MATLAB style, starting from 1. Here's the cool thing about this, and I'm gonna use the MATLAB. This is the one time in the one algorithm where I think array starting from 1 is actually not dumb. So if you wanna find out in a level order traversal when you're inserting what the child node is of any node, you take that index, if you're using starting from 1, you multiply times 2, and that gives you the index of the child node, of the left child node, and then you add 1 to that, you get the right one. So for example, let's take B. B is index 2. If I want to find out B's children, I'm going to take B's index, multiply times 2, and that'll give me the left child index in my input array. So 2 times 2, which is equal to 4. And look at that. That's actually right. Furthermore, if I want to have the right child, I was left, I would hit that one. Then I can simply do +1. So B's index times 2 plus 1 is the right child. And that's also true, as you can see.
From 0 though, you can just do it at 1 or at 2.
That's what I was going to say. If you want to stick to starting from 0, then all you got to do is do the times 2 plus 1 and times 2 plus 2, which is weird for me, and I usually remember this way. So I think in my implementation on the homework, I don't think in the skeleton code this is there, because I think this is something you're adding in. But if it's there, and you see why things are starting from 1, that's why. Because I just, once you get set in your ways, it's hard to change. So you know, as you can see, the child of something that is like E, for example. E has no children, right? 5 times 2 is 10. When the child's index is out of bounds or it has a percentage, it means that there's no child. So make sure you do that check. Otherwise, you're going to be axing out of bounds and you're going to seg fault. So that's your mission. Can you achieve it? Can you save James Bond so he doesn't die? So
What if you don't accept the mission?
then he dies. I mean, hey, it's a free country, right? You don't have to do the assignments.
No, James Bond is British, they're not free.
The British, yeah, they're not free, that's true. But we're free. Okay. So any questions on anything? Traversals or assignment?
What did the assignment do?
So, good point about that. Oh, and there's one more thing I still want to tell you.
Oh, yeah, next.
So that's right. But so the assignment, this assignment is not due until after spring break. It's due the day before. Actually, it's due like the Saturday before spring break ends because I shifted them so that like they're not all due the same day. They're due like one day after the other.
Thank you.
But ultimately, I don't think you should wait until that long to do them. In fact, I did this because like you can do them now and have a free spring break, or you can just procrastinate and have your spring break be like full of assignments. You'll have assignments 6, 7, and 8 more than likely due before spring break comes back. So that's 3 assignments in 2 weeks. Because technically 6 and 7 are one assignment. I just split them for clean purposes. Like again, this is 40 lines of code you're really only writing. So okay, so I'll stop the recording now. Thank you for watching. This video was sponsored by coronavirus.